Hello and welcome to our exploration of probability theory, where we introduce some mathematical concepts that allow us to make sense of uncertainty and randomness. In this video, we will explore the sum and product rules of probability using a straightforward example, followed by Bayes' theorem. This discussion is designed for those with a foundational understanding of mathematics, aiming to provide a clear and concise explanation of these fundamental concepts. Let's begin with a simple scenario involving two colored boxes, one red and one blue, each containing a mix of apples and oranges. The red box contains a majority of oranges, while the blue box has more apples. From this example, we'll derive the sum and product rules of probability. First, consider the probability of selecting each box. If there is a 40% chance of picking the blue box and a 60% chance of choosing the red one, we express these probabilities as follows. Notice that the sum of these probabilities equal 1, signifying that they are a mutually exclusive and collectively exhaustive set of outcomes. Imagine that we repeatedly choose a box and then a fruit from within, recording our selections each time. After many such trials, we create a contingency table reflecting the outcomes. From 100 draws, we observe the number of apples and oranges selected from each box. The table summarizes the results of the experiment. For example, we picked 15 apples from the red box and 30 apples from the blue box. Similarly, we selected 45 oranges from the red box and 10 oranges from the blue box. The totals on the right and bottom indicate the overall number of times a particular type of fruit was chosen or how many fruits were taken from each box, respectively. This table helps us understand the distribution of our selections and can be used to calculate probabilities for different outcomes of the experiment, such as the likelihood of picking an apple from the red box or an orange when we know the box is blue. We'll start with the joint probability. The joint probability calculates the likelihood of two or more events occurring together and at the same point in time. The joint probability that the chosen box will be blue and the chosen fruit will be orange is written as follows. In our example, it can be calculated by the number of times we chose an orange in the blue box, so 10 times, as a fraction of the total number of trials, which is 100. We now come to the sum rule. Say we want to know the probability of choosing an orange regardless of the box. This is calculated by summing the number of times an orange was chosen in the red box, so 45 times, and the blue box, so 10 times, divided by the total number of trials, which is 100. We sum the probabilities of picking an orange from each box individually. This is the essence of the sum rule. The probability of a single outcome, regardless of other variables, is the sum of the joint probabilities over all values of the other variables. If we considered only the trials where fruit was chosen from the blue box, then the fraction of trials for which an orange was chosen can be written as follows. This is called the conditional probability and can be verbalized as the probability that the chosen fruit is an orange given that the box is blue. The conditional probability can be calculated by taking the number of times we chose an orange within the blue box, so 10 times, as a fraction of the total number of fruit drawn from the blue box, so 40. Finally, we arrive at the product rule. The joint probability can be expressed as the product of the conditional and marginal probabilities calculated earlier, as seen here. The product rule simplifies calculating joint probabilities as the product of one event happening given another and the probability of that given event occurring independently. Before we move on to Bayes' theorem, we'll first recap what we have learned so far. The sum and product rules help us rate joint, marginal, and conditional probabilities. The sum rule tells us how to find the probability of a single event by summing over a joint distribution, while the product rule shows us how to find a joint distribution by multiplying a conditional probability by the probability of that condition. Note that the notation has changed slightly here. In these equations, Px denotes the probability distribution over the random variable x. In some cases, we might not have access to the full joint probability distribution of the problem's random variables. In this case, Bayes' theorem helps us calculate conditional probabilities. Bayes' theorem plays an important role in machine learning and allows us to write the relationship between conditional probabilities in the following manner. Here, the denominator can be viewed as being the normalization constant required to ensure that the sum of the conditional probability of y given x over all values of y equals 1. This can be explained by using the sum rule, where the denominator in Bayes' theorem can be expressed in terms of the quantities appearing in the numerator as follows. Let's apply Bayes' theorem in an example. Suppose we are told that a piece of fruit has been selected and it is an orange, and we would like to know which box it came from. This requires that we evaluate the probability distribution over boxes conditioned on the identity of the fruit. In our example, we have seen how we can calculate the probability of selecting a certain fruit given the color of the box, but we do not know how to solve the conditional probability when it is reversed. What is the probability that a certain box was selected, knowing we selected a specific fruit? We can solve this problem of reversing the conditional probability by using Bayes' theorem as follows. Then, from the sum rule, we can determine the probability that the selected box was red, given that the chosen fruit was orange. If we had been asked which box had been chosen before being told the identity of the selected fruit, then the most complete information we have available is provided by the probability of selecting a box. This is called the prior probability. It is the probability available to us before we observe the identity of the fruit. Once we are told that the fruit is an apple, we can then use Bayes' theorem to compute the probability of selecting a specific box given a fruit, which is called the posterior probability. It is the probability obtained after we have observed the fruit. Note that in this example, the prior probability of selecting the blue box was 40%. We were more likely to select the red box than the blue one. However, once we observed that the selected fruit was an apple, we found that the posterior probability of the blue box was now 67%. It was therefore more likely that the box we chose was in fact the blue one. This makes sense, as the blue box contains far more apples than the red one. Bayes' theorem is a powerful tool for solving problems such as this example, as well as more advanced problems. However, it is important to remember that if we happen to have access to the full joint probability distribution of all the random variables that we care for in our setting, then the sum and product rule would suffice, as we would not need Bayes' theorem for this specific problem. Thank you for joining me in this concise introduction to probability theory. Until next time.